Welcome to the American Rock Mechanics Association's Underground Storage and Utilization Technical Communities webinar series. Today, we are privileged to have Dr. Jonny Rutqvist, who is a senior scientist and head of the Hydrology Department, Energy Geosciences Division at the Lawrence Berkeley National Laboratory. He holds a PhD degree in engineering geology from the Royal Institute of Technology in Sweden. For over 30 years, Dr. Rutqvist's research has been focused on geomechanics and modeling of coupled thermal, hydraulic, mechanical, and chemical processes in geological media for a wide range of geoscientific and geoengineering applications, including geologic carbon sequestration, nuclear waste disposal, geothermal energy extraction, unconventional oil and gas, and underground energy storage. Dr. Rutqvist has authored over 200 peer-reviewed journal papers and is a four-time recipient of awards from the American Rock Mechanics Association. Today, Dr. Rutqvist will present a webinar on coupled thermal hydromechanical processes associated with nuclear waste disposal in different host rocks.
So thank you for inviting me to do this presentation. So now I'm going to talk about the permanent storage of nuclear waste. And this is about the coupled THM processes associated with the nuclear waste disposal in different host rocks. These include crystalline, hard rock, and in this case, they would place the waste canisters in tunnels in the crystalline rock, and those would be backfilled with bentonite backfill swelling clay. And this is an important barrier in the crystalline rock disposals. Then the second one is argillite, softer rock. And in this case, you also had cases with bentonite backfill. And finally, salt formation, where you have the waste in tunnels, but then they are backfilled with crushed backfill. So we have been developing models to study all these kind of formations. And if you look at the THM couplings, so this shows an overview of the THM couplings, and in the case of nuclear waste disposal, these are typically thermally driven. So you have an increase in temperature, and this is driven the coupled processes. So for example, you have an increase in temperature, you get the thermal expansion from T to M. And between T to H, so from temperature hydrology, you have also changes in fluid density or fluid expansion that causes pressure changes.
Faster.
And then you have from H to M, you have moisture swelling, actually swelling of the bentonite when it gets resaturated. This is also an important process. And then from M to H, you have changes in porosity and permeability, which will affect the transport properties. So coupled processes, I believe, have been part of the nuclear waste programs already from the beginning, already from the 1970s or even earlier. However, the term maybe was not mentioned, but actually in the early 1980s, there was some workshops in Berkeley on coupled processes associated with the nuclear waste disposal. And this was summarized in an edited book by Chin Futsang in the 1987. So it's very interesting actually to read that book, what they did all in that early time. Then in the 1992, the International Decovarics Project was launched. So this is a development of coupled processes and their validation against experiments. And so this project typically involves about 10 research organizations from different countries, such as Japan and European and United States and Canada and so on. And this is funded by funding organizations that are nuclear waste disposal implementers or regulators. Typically about 10 organizations involved. And in this project, we have been studying a lot of, doing modeling of a lot of in situ THM experiments. So those have also been important actually in the nuclear waste, this kind of research, and starting maybe with the stripper mine in Sweden in the early 80s. And in addition, you need, of course, a lot of laboratory experiments, supporting laboratory experiments have been conducted on granite, claystone, bentonite, and salt, and so on, for developing the constitutive models and learning about the fundamental processes in this kind of milieu. I mentioned the experiments, field experiments. So these are a list of the field experiments in underground research laboratories that has been done in the Decavallix project. Starting with Fanay-Aucher in France, which at that time they considered the granite in France as a host medium. And if you go down to the list, if you go down to the third one, the drift scale test at Jaka mountain. This one you can see also illustrated down to the left here. So this is still the world's largest underground heating experiment that has been conducted. And with a very high heat power and high temperatures goes up to 200 degrees in the host rock. And they monitored the THMC responses in several thousand sensors in boreholes, as you can see there. So that includes the temperature, mechanics, hydrology, like permeability changes, and so on. And this experiment was then conducted at Jaka mountain, which is an unsaturated fractured rock. The fourth one is the FEBEX in situ experiment at Grimsel test site that you can see down to the right. So this is very much focused on the evolution of the bentonite buffer and the interaction with the host rock, which is granite in this case. And if you can see the early time, many experiments were focused on hard rocks, whereas more recently there's been more focused on claystone or shale, such as the Monterey laboratory in Switzerland and at the underground research laboratory in Bure, France, where they're looking at the Cox claystone. And but in all these experiments and many of the experiments, we look at also at the bentonite buffer and the host rock. And this is actually related to the multiple barrier functions of a repository. So here you can see an overview of those barriers. So you're starting with a copper steel canister, which should isolate the waste. And then this is placed in a tunnel deep down underground and embedded by a bentonite buffer that should be tight. It should provide a mechanical stability to the canister. It should retard the arrival of water and corrosive solutes to the canisters. And you should also retain and retard migration of radionuclides if released from the canister. And then you have the bedrock itself, which should provide a stable chemical and mechanical environment and retard radionuclides if released. So these are the barrier functions we need to study with a coupled process model. And here we can see an overview of coupled processes that can take place in such a system. So this is a system with a waste canister placed in a tunnel and embedded in a bentonite buffer. So what you typically see when you place the hot waste in the bentonite buffer is initially saturated at about maybe 65%. So you have heating of the bentonite and the rock. Second, you have the drying of the bentonite close to the heat to the waste canister, because you have a thermal gradient from the waste canister out through the bentonite. So you get evaporation of liquid into vapor, and that is actually transported the vapor out to the cooler regions, where it again is condensed into liquid. At the same time, if you see number 3, you have wetting and swelling of the bentonite. So you have wetting from the host rock, and the rate depends on the permeability of the host rock. And then you get the swelling of the bentonite. And number 4, you have thermal stress and deformation taking place in the host rock. And then number 5, you have thermomechanical induced changes in permeability, which need to be evaluated to see the impact on the transport properties. So these are, I say, early time. So with early time in this context, I mean hundreds to 1,000 years maybe. But then for the long-term performance assessment, what are the impact? So if you look here, this is after the resaturation of the buffer and the heat has decayed, and then you want to see what is the impact over from up to like 10,000 years, and or even longer. So number one, what is the impact on the protective function of the bentonite buffer? And two, what is the impact on the rock bentonite interface? And 4 and 3, on the impact on the excavation disturbed zone. Will we have changes? Will we have permanent changes in permeability, which is number 4, that could impact the transport properties. So ideally, you want to have the buffer 100% saturated. You want to develop the swelling stress, which typically can be maybe 5 megapascal, and you want to have all openings sealed, like open fractures and so on, sealed. So this is if it worked as intended. If it does not work as intended, or if there's a breach of barrier as illustrated here, for example, if you have a breach of the canister caused by corrosion, maybe diffusion of the radionuclides through the bentonite, which may be not perfectly, if it's could even be fractured if it's dry, and out into the host rock, and maybe if you have open fracture, you can have advection along the fracture. So this is something we want to avoid. We want to make sure that it doesn't happen. And so these are where the coupled THM processes comes in. We want to study these processes and see what is the potential impact on the flow and transport properties. I'm not going to talk about flow and transport. I'm going to talk about what you see to the left here, the coupled THM processes and how that may impact over time. So also in this context, I like to mention some of the concept in nuclear waste disposal. So thermal management and temperature limits. So typically when you design the repository, you see how long time you need to have interim storage on the ground before you can put down the waste because it's too hot, and also how densely you can pack those canisters and how densely you can have the distance between tunnels to actually manage the temperature. So they don't want to have too high temperature in the EBS, engineering barrier system, you don't want to have damage there. So usually they have some temperature limits on the waste canister, buffer, and host rock. And for crystalline rocks, such as in the Swedish, Finnish, Korean, they usually say that the temperature at the canister surface should not exceed 100 degrees C to assure chemical stability of the bentonite, because if it's high temperature, there may be some mineral transformations that can affect the bentonite swelling, and permeability could increase. For argillite host rock, such in the Swiss concept, they actually tolerate higher temperature than 100 C, because the host rock in this case is considered a primary barrier. So they're very tight, argillite or shale. And then they instead have a temperature set for the opalinous clay to be the maximum helio temperature of about 80 C, thereby excluding thermally induced geochemical processes that could be detrimental to the host rock properties. So this is we can keep in mind. Okay, so this one shows kind of a workflow for coupled THM modeling. So typically, so we have a coupled THM model. So in this case, we have been using simulator based on our TUF2 multi-phase flow simulator developed here at the Lawrence Berkeley lab, and linked that to Flux 3D geomechanical simulator. And using this coupling, we have done coupled THM modeling of all these kind of systems. And a big part of it is actually to develop the constitutive models and implement constitutive models into the simulator. For example, for bentonite, you have the Barcelona basic model or the Barcelona expansive model we have implemented into the TUF Flux simulator. And in this case, you see that we then run, you then have the models that based on laboratory scale experiments on bentonite, for example. And then you run the validation experiments. So you're running these big scale underground heating experiments. So this one is the full scale emplacement test in Opalinus clay at Monterey. This is also a big experiment. We have 3 simulated waste canisters. These are heaters. They're heating up to 140 degrees C, and it's emplaced in a bentonite buffer. Down at the bottom, you see the evolution of temperature and relative humidity. So the squares are the measurements done in situ, and the lines are the model simulations. And typically you can predict temperature very well. And then to the relative humidity, you see this typical response of drying near the heater because of evaporation in the early time. So you see the relative humidity starts at 30%, then finally goes down to about 20 or 30%. Whereas at the rock boundary, you have an inflow from the host rock, which is quite slow in this case because it's a low permeability host rock, Opalinus clay. But it's going towards fully saturated, and it will take a long time before this buffer is fully saturated. So then we have that, and then we try to use the material properties we developed and validated here, and then we try to do the long-term simulations. So in this case, we use a heat source for a waste canister. In this case, I'm doing a 2D model based on repetitive symmetry. So this would actually represent emplacement tunnel at the center of the repository. And we have the heat load here per meter drift. Here we can see the results of temperature and liquid saturation. And these are taken at some point. So you see point V1 is next to the heater, to the waste canister. The red line for the temperature graph on top, you can see that the red line goes up to 91 degrees C at about 50 years. So that's the peak temperature that at the waste canister, and then it goes down again because the heat decay from the waste package is going down. But then you can see the purple line. You can see that it peaks at about 1,000 years at 65 degrees. So this is at the point 10 meters from the tunnel. So this could represent kind of the average temperature in the host rock of the repository. And this is affected by all the temperature decay from all the waste canisters, and you reach this kind of average temperature of 65 degrees at 1,000 years. Then down below, you see the evolution of liquid saturation starting at 65% in the buffer. So this is for one point V1 close to the waste canister. So that's the red line. So you see the typical drying from 65% to 50% after 3 years. And then it gets resaturated. And you can see the blue line, which is placed at the rock boundary. There you get inflow from the saturated host rock. And the buffer gets fully saturated after 25 years here. So these are kind of important to note here for the thermal management. You have what is the peak temperature. There are some criteria for that one. And what is the time to the peak temperature and time to full saturation. Time to full saturation is important because that's the time when you have fully developed swelling stress in the bentonite, which I will talk about later. If you then look at the pore pressure and stress, so look first at the pore pressure on top. You can see that the pore pressure, this is for 1 point within the tunnel, within the bentonite repository tunnel, and for 1 point 10 meters away. You can see that the pressure goes up actually very high, up to 8 megapascal after 2,000 years. And this is actually correlated very well with the temperature changes in the host rock. So this average temperature I talked about. So this is caused by thermal pressurization. So this is because you have thermal expansion of fluids inside the host, the clay stone, and because the thermal expansion of the fluid is much larger than the thermal expansion of the host rock, so that's why you get the increase in pressure. And this increases, and then it starts going down, then the temperature goes down, and also it's a pressure diffusion due to you have some permeability. Then we look at the stresses down below. You can see that the total stress, and this is for a V2 inside the buffer actually. You can see that the total stress increases and peaks also at 2000 years. So this is exactly very much correlated with the thermal pressurization and the pressure changes in the host rock. And this is caused by then pore-elastic stress in the system. You can also see what they say there is the effective stress. So that's the total stress minus the fluid pressure. And that effective stress is actually equal to the swelling stress in the bentonite. It is also affected by thermal stress in the bentonite. This is why you see a decline in effective stress from about 50 years going to 100,000 years. You see that there's a decline in effective stress. This is due to cooling shrinkage of the bentonite buffer. So here there are some points to look at the peak temperature, the time to the peak temperature, and time to full saturation I mentioned before, but then you have the peak pressure. So here you see the peak pressure is about 8 megapascal. The vertical stress for this one for weight of the overburden was about 11 megapascal. So this is still below that, but sometimes if you would put for example, the drifts closer to each other, you would could easily reach a pressure above the 11 megapascal isostatic stress. And that means that you actually could induce hydraulic fracturing in the system. So that's something you really want to avoid. Time to peak thermal impact. So this is also something I will talk about more, because that happens when you have the highest temperature in the host rock, which you have said occurred like 1,000 years. And then whether we have sufficient swelling stress and swelling stress in time. This is also important for the stability of the tunnel walls, which I will present in the next slide here. So this is to the left, you see a plot of the stress path for 1 point V3 in the host rock in the EDZ just above the tunnel. So you see the max on the y-axis is the maximum principal stress, and in the x-axis is the minimum principal stress. So this is the stress path of the minimum and maximum principal stress. And then you can see the yield surface. So this is for the rock matrix in this bedded material. In the model, I have a bedded material model for the host rock using the ubiquitous joint model in Flux 3D. So you have a different shear strength for the weak planes that are oriented horizontally here. And then you have the rock matrix, which has their own properties based on laboratory tests that have been conducted for the rock at the Monterey opalinous clay. So you start after excavation, there is a low minimum principal stress because that's the radial stress in this case, and then you have the tangential stress is the maximum principal stress. And then from excavation to 1 year, it starts to moving towards the yield surface, but don't really reach it. And then from 1 year to 10 years, you see the stress moves away from the yield surface, so it becomes more stable. And this is actually caused by the swelling of the bentonite buffer. So here you can see the importance of having the swelling of the bentonite buffer actually to support the excavation walls and keep it tight. And then you can see that the stress starts going down to 100,000 years is going down when you have cooling of the system, and this is due to the cooling shrinkage of the bentonite. So the EDZ evolution is here impacted by the thermal pressurization, which causes a lot of stress changes. And you have this thermal stress, and you have the wetting-induced bentonite swelling of the bentonite. We also looked at similar processes for crystalline rock. So this is for the KBS3 system used in Sweden. And so in the crystalline rock, you will have higher thermal stress because it's hard rock. So the thermal stress will depend on the thermal expansion and the stiffness of the rock. And in this system for the KBS3 vertical, you have the emplacement. The canisters put in vertical emplacement deposition holes emplaced and in a buffer, and then you have the tunnels on top, which are backfilled with a mixture, maybe mixture of bentonite and crushed rock. So this is the system, and here we then look at the potential for inducing failure in the host rock. And you see the one for the intact granite, you have a lot of red areas around the deposition hole. And this is actually where you could have thermomechanical spalling. And in this case, for intact granite, actually the resaturation is, there is no fractures actually close to this deposition hole and this tunnel. So there is only intact granite. So we have a very low permeability and very slow resaturation of the buffer. And there was not enough swelling stress before you got the thermal peak. And that's why you see some increased thermal spalling in that case. Whereas in the case to the right, this is for a fracture granite. So there you can have a more rapid resaturation of the buffer, and swelling stress develops, and there was no additional damage to the host rock. So again, this shows that it's important to achieve the resaturation and swelling of the buffer before this thermal peak stress. And this is also there is also impact on the larger scale. So here you can see an illustration where you see the row of emplacement tunnels, which are heat released from there. So then you get a general temperature change in the system, delta T. This can also cause a change in fluid pressure due to thermal pressurization if you are in a host rock that has low permeability, such as the argillaceous claystone. And what you see then is that you have an increase in horizontal stresses. This is caused by porolastic stress and could be caused by the thermal stress in the case of a hard rock. So if you, at the same time, the vertical stress stays almost constant because that's dictated by the overburden and the free moving ground surface. So the result is an increase in shear stress in this area, which means that you might induce the activation of shear activation of pre-existing fractures. And as I said before, if the fluid pressure exceeds the overburden stress, you may actually induce hydraulic fracturing. So these are something that needs to be actually considered very carefully in the thermal design of the repository. So not only the temperatures close to the drifts or in the bentonite is important, but actually the average temperature in the host rock may be a limiting factor for the thermal management. And this kind of horizontal stress increases, of course, also impacts the stress around the tunnels. You may have high stress concentration on the top of the tunnel. You may have stress relief on the side of the tunnels. And this can happen 1,000 years after the repository closure, because that's when you have the highest thermomechanical and porolastic effect from these kind of average temperature changes in the host rock. So again, it's important to have the buffer supporting swelling at the time. Finally, I'm going over to for the salt formations. And in this case, this system is, there are some good properties for salt formations. The most important maybe that it could be self-sealing and healing. So it can actually, due to creep, long-term creep in the salt, you can actually completely solidify after some time, you close all the openings, so completely encapsulate and isolate the waste in a practically impermeable medium. So in this case, the salt creep is important with enhanced temperature. And in this case, we see one design from Germany, where they consider the emplacement of the waste in tunnels that are then backfilled with salt backfill. So we need models that actually can model these kind of processes, so creep over several 10,000s of years, and it should be include a temperature dependency of that and damage and so on that could occur. This we have done, we are doing also with Tough Luck, and here we work with a group in Germany, the Klausa University, Professor Lux and his co-workers. They have developed a very nice constitutive models for salt host rock that includes the elasticity, viscoplasticity, and damage. So you can have a damage if you have high deviatoric stress developed around the tunnels. The permeability can increase, but then as time goes on, these kind of deviatoric stresses would tend to even out due to creep deformations, and you can have a healing, so reduced permeability gain. So this is done, and here we looked at the large scale in situ experiment that was conducted at Esm in Germany. This was part of the Bambus project, which was I think a European Union funded project probably in the early 90s. Or this field experiment, and you have temperatures up to 200 degrees at the waste canisters here. And this heating took place for about 8 years. In the middle, you can see the temperature evolution. So the solid lines are the modeling, and the symbols are the experimental data. But I think most important is to see down to the right. You can see the evolution of porosity as a function of time. And what you can see is that the compaction is happening much faster in the heated area. So you can see the heated area, you have a porosity going down in the crushed backfill from 35% down to 25% in 8 years. And so this is caused by the closure of the tunnel, which is dictated by creep deformations. And this is accelerated by the heat in this case. So this actually involves also large strain calculations to be included in this kind of model. So this is from the field experiment. And then we go over to looking at the long-term effects from this model. Again, we assume a heat source from waste canisters. We look at the THM modeling of creep convergence of the tunnel and compaction of the backfill. And maybe one important is how long, when do you have the complete sealing of the system? So you can see the evolution of the backfill here down there, starting at a porosity about 35% from beginning, and then progressively at the 10 years you have about 20%, and then if you go to 10,000 years, it goes down to very small, like a fraction of a percent, which is similar to the properties of the host rock salt, natural salt actually, so very, very tight. But here you still see that after 1,000 years, according to this model simulations, there is a 10% porosity would still be some increase in permeability. And so these are important to study, and it's also, of course, some uncertainties in how this actually backfill actually can compact when it goes to very low porosity. And there are experiments ongoing looking at the compaction of backfill and as a function of temperature and moisture content. So to summarize this simulation, this presentation, we have seen there is a lot of different key THM processes for different host rocks. So for crystalline rock, you have the backfill, saturation, and swelling of the bentonite is important. You have the thermal stress are important because of the hard rock. And this can occur, as I said, a long time after emplacement. You have the evolution of EDZ permeability. For oilite, rock softer and low permeability. Thermal pressurization comes into the picture, which is much more important and needs to be carefully evaluated. For salt, you have the backfill compaction and sealing. You have the thermally enhanced creep. It's important consideration. Here we can also have thermal pressurization. Actually, our simulation showed that strong thermal pressurization. But in this case, you have the medium that has very low porosity, fraction of a percent. So we're not sure how important that is then, actually. And you have the backfill and EDZ permeability to evaluate. And to the left, you see also the illustration again, the general evolution where you have the peak temperature of the host rock that can occur hundreds of thousand years after emplacement. So this is important, not just the near field temperature. And this is what I want to say, that actually the repository average temperature, which is lower than the near field peak temperature, may be a limiting factor for the thermal management of repository design. And this is something that I think needs to be pay more attention to in the future. So that's my presentation. Thank you. Here are some of the references. You can find more details on the presentations I made.
Thank you, Jonny. I'm sure that he's happy to answer your questions, and there are several already in the chat.
Okay. Let's see. Where I try to find the chat.
Mine is centered under the screen.
Oh, okay. Okay, I can see it now. Okay. Okay, I can go to the first one. Okay, one from Alexander Gouin. How much does the size of the excavation disturbed zone impact the effectiveness of the facility? Does it support an argument for less disruptive excavation method, TBM? Yes. So yeah, I mean, they have been studying this a lot. I know at the Esm Hard Rock Laboratory in Sweden, where they look at the disturbed zone when they're using drill and blast, and when they use TBM, and definitely when they use TBM, you get a much smaller disturbed zone. You don't get as much fracturing. So I think that's what they're going to use to excavate their repository tunnels, the TBM. So that's a yes to that. And next one, how are you modeling multi-phase flow through fractures in the host rock in the Continuum Flux 3D model? So we are not using Flux 3D for multi-phase flow. We are using the TUF2 model. So here we linked the TUF2 multi-phase flow simulator with the Flux 3D model to be able to model a multi-phase flow. And actually, this was originally developed for the Jaka mountain project in the United States, where you have very strongly coupled multi-phase flow processes. So in that case, we have an unsaturated host rock, and temperatures were up to 150 degrees or 200 degrees. So you have boiling and very strong multi-phase flow processes. And from beginning, they actually used the TUF2 code for the performance assessment of the Jaka mountain repository, but they did not. They then wanted to know what's the impact of the mechanical effects on the fluid flow. So that's actually the original idea why we linked to the TUF2 to Flux 3D to do the modeling of that system. And then we used the TUF Flux model for other applications such as carbon sequestration. And have you run any discontinuous model in your coupled THI model 3 given the dramatic increase in temperature changes and area around the cans? Have you modeled cans that are under these conditions, low buckling? I personally have not done the modeling of the like if you have a shear, you can have a shear fault or shear deformation across a canister or across a canister. But I know that, for example, in the Swedish repository system, that's something they look at kind of carefully, and they actually use, they have used 3DEC, I guess, 3DEC or Abacus for modeling the shear through the waste, through the deposition hole where you have bentonite and you have the waste canisters, so they see how much shear could you have before you can cause significant damage to the waste canister. I think that then they develop some criteria that you can have a like 10 centimeters shear across deposition hole. And of course, in there are also in the Decovalex project, we are studying this problem. We use many different kinds of models, both discrete fracture models and continuum models to simulate the similar problems. And also in the Swedish, where they have a fractured rock system in granite, they use actually 3DEC for modeling the thermomechanical changes. And they are also sometimes using 3DEC for different applications, but in this case, I mean, we want to do in this case, when we want to model the bentonite buffer and their host rock, we need actually a multi-phase flow simulator that have to link to a geomechanics code. And then Nikita, for long-term simulation, creep behavior could be significant. Is it incorporated in the model? So it's incorporated in the salt simulations, but actually this is a good question for the clay host rocks. We did not include it in those large-scale modeling I showed before, but I'm actually going to start doing that this year, because I think that's important. Could be important also for the case where you have argillite, not only for salt. For salt, it's obvious that that's driven by creep deformation, and there we simulate it. But maybe also in the case of a clay or shale repository, especially if you have these kind of very ductile shale, like the Pore shale or in the US, or that could be significant, and it's also related to the sealing around the tunnels. So this is important process. So this is going to be done in the future. And the next question, consider the significant change in pressure, temperature. Does model consider changes in material properties? Hydraulic properties, compressibility due to heat. Consider significant changes due to heat generated. Do you set the initial subsurface rock property constant? They are not. So it depends. I mean, of course, for the bentonite buffer, we could use some of the simulation I showed where we use the Barcelona basic model or Barcelona expansive model for the buffer, bentonite buffer. So then the stiffness is strongly correlated with the saturation of the buffer. And it's also correlated with the confining stress on the buffer. So this one is strongly nonlinear. And then for the host rock, we consider, I mean, depends on the different simulations, but we consider changes in permeability with stress using different models for that, depending on what we want to study in that particular simulation. And but I think there could be more to do, especially when it comes to, of course, in salt, there is a lot of changes, temperature dependent changes in the properties, and that is considered in the very advanced constituted model there. But I think it's important, I think, also to consider these changes. Principal stress rotation in the overburden, hence low angle shear fracture. Did you observe that in the salt and swelling clay model? I tend to think that ubiquitous joint model will probably yield slip under stress rotation did you observe yield in there? So in this case, the ubiquitous for the shale, I use the ubiquitous joint model for the shale because that's kind of an anisotropic material, and the shale beddings are horizontal. So then we see some yielding next to the tunnel. But then you saw that the illustration where if there is a low angle fractures, I think that's more, it could also be in shale, but I think it's mostly for granite and things like that, where you have discrete fracture network. And I think we have, in this model, we didn't model it explicitly, the shear activation, but I think that's also an important issue in the future, especially for granitic rock mass. If you heat up that big area in a granitic rock mass that is, you have fractures and some minor faults, I think one issue that has not been talked so much about is the potential for induced seismicity. As you have seen, there is a big problem or big issue in geothermal when you have this kind of a brittle host rock, and also in the crystalline basement for wastewater injection. So in this, I think there could be cases where you could actually generate the felt earthquake that could be felt, maybe not a very big one, because this is still quite a limited area, hundreds of meters that are heated. But if you, after 1,000 years, the population starts to feel some induced seismic events, that could be some concern. So I think that's something that should be paid more attention to in the future, I think. And this is also related to this, what I said about the average temperature changes in the system will be important could be an important factor, and these large-scale THM changes in the host rock that should be considered in the design of the repository. I think that's the last question on the chat window.
Jonny, I wonder if you may offer some closing thoughts on the issues.
Closing thoughts. I mean, these are important for the nuclear waste disposal, and not only the near field and bentonite processes and so on, but also the large scale THM effects are important. This is about coupled processes, and it's important to all kinds of applications, as you have seen. When I started like 30 years ago, I only worked on nuclear waste disposal, but nowadays I work on many different applications area where actually coupled processes has become important, such as carbon sequestration and geothermal and so on. And actually we have a upcoming conference that I want to advertise. This is called the CoFrac 2020. This is about coupled processes in fracture media. It's going to be held in November 11 to 13. It's going to be completely virtual. So we will talk about coupled THMC processes in fracture media. And we have a lot of good keynote speakers and invited speakers and emerging scientist speakers to that conference. So you can contact me if you want more information about that upcoming conference.
Thank you, Jonny. I'd like to end this webinar by thanking the co-chairs of our underground storage and utilization technical community, Osman Hamid from Aramco and Taha Hussein from Shell. I'd also like to thank Genghan, Joe Morris, and all of our friends with ARMA who have supported this webinar series. This concludes our webinar, and thank you for joining us and participating today.
Thank you very much. Nice to see you again, Jonny.